measure of an empty set is 0. Okay. So this will be equal to m star of A intersection R plus, since A intersection R complement is equal to null, I can write this null as m star of A intersection R complement. Okay, so if you observe this, this is from definition of Lebesgue measurable set. I can say R is Lebesgue measurable set. Okay, so from previous property, we know that if any set is Lebesgue measurable set, then its complement is also Lebesgue measurable set. So for R, the complement of R is 5. From previous property, I can say 5 is also Lebesgue measurable set. This is true for every subset of A of R. So from this we can conclude that both R and 5 are Lebesgue measurable set. So now you have this situation. This is set of all Lebesgue measurable set. Inside this there is one box, consider like that for a better understanding. Inside this box you have R. Since R is Lebesgue measurable set, you have 5. 5 is also Lebesgue measurable set. And if any set E is there, means its complement is also there in this box. Okay, so I can write like this. If I consider this box, this is for just for better understanding, I am writing this picture. So if I consider this is my Lebesgue measurable set box, inside this box I have 5, R, E complement, everything is there. Okay, so let's see what are the other things are contained in this box. So this is the basic things we got from our property. So let us let us check what are other things are contained inside the box. So to check what are the other things there inside our box, I am proposing this theorem. If a set has Lebesgue outer measure is 0, then that set is Lebesgue measurable set. So that means if any set has outer measure is 0, then that particular set is also there inside our box. So let's check this. Suppose I will consider E is any set and outer measure of E is 0. So what we need to prove here? To prove E is Lebesgue measurable set. So from Lebesgue measurable set definition, I can start with if A is any subset of R. From this figure, I can say A intersection E is subset of E. A intersection E is a part of E. So from that I am writing A intersection is subset of E. So from monotonicity property of M star, I can write M star of A intersection E is less than or equal to M star of E. I will call this inequality as 1. So again from the figure, I can write A intersection E complement is subset of A. This A intersection E complement is subset of A. So again from monotonicity property, M star of A intersection E complement is less than or equal to M star of A. So these two are from monotonicity of M star. Monotonicity of M star. Since all the quantities are positive, because outer measure is defined to be positive, I can add these two inequalities. That is M star of A intersection E plus M star of A intersection E complement will be less than or equal to m star of E plus m star of A. The given thing is, if I consider E as any set, then outer measure of that set is 0. So I can say this m star of E is 0. From this I can write m star of A intersection E plus m star of A intersection E complement will be less than or equal to m star of A. In other words, I can say m star of A is greater than or equal to m star of A intersection E plus m star of A intersection E complement. From countable subadditivity property, it is known that m star of A is always less than or equal to m star of A intersection E plus m star of A intersection E complement. So from inequality 3 and 4, I can say m star of A is equal to m star of A intersection E plus m star of A intersection E complement. This is nothing but, from definition of Lebesgue measurable set, I can say E is Lebesgue measurable set.